So in this section, we'll talk about application of integration, okay? Physical application. So density and mass. Density is the concentration of mass in an object and is usually measured in units of mass per volume. For example, gram per centimeter cube. An object with uniform density satisfies the basic relationship. Mass is equal to density times volume. So that is when an object with uniform density. But, when the density of an object varies, this formula no longer holds, and we must appeal to calculus. That is why to start, we will do mass of a one-dimensional object. Suppose that a thin bar y is represented by the interval a is less than or equal to x and x is less than or equal to b with a density function rho. So this symbol name is rho, is a Greek letter, but you can call it p. It's just a symbol, okay? With unit of mass per length, the mass of the object is m is equal to the integral from a to b rho x dx. So this is the formula for mass. Let's jump and solve the first example. A thin 2-meter bar represented by the interval 0 is less than or equal to x, which is less than or equal to 2, because the bar is 2 meter, is made of an alloy whose density in unit of kilogram per meter is given by rho x is equal to 1 plus x squared. What is the mass of the bar? Density in unit, okay? So again, we will just solve. Then m, the rule will not change. We said m is what? The integral from a to b rho x dx, which both are given to us. A is 0, b is 2, rho x is 1 plus x squared dx. And this one will give us x plus 1/3 x cubed from 0 to 2. If you substitute, we'll have 2 plus 2 to the power of 3 is 8. 2 plus 8 divided by 3, which is 14 divided by 3. So our mass will be 14 divided by 3. Okay, let's move to work definition. Before I give you the formula for work, let's talk about work. Work can be described as the change in energy when a force causes a displacement of an object. So which mean, again, the basic formula for work could be work is work is equal to force times distance. But calculus enter the picture with variable forces. So if the force change, suppose an object is moved along the x-axis by a variable force F that is directed along the x-axis. So how much work is done in moving the object from the object between x is equal to A and x is equal to B. So that's what this formula, the work done by a variable force moving an object along a line from x is equal to A to x is equal to B. The direction of the force is W, which is work, is equal to the integral from A to B f of x dx. Let's go ahead and do the first example of this. Okay. Suppose a force of 10 Newton is required to stretch a spring 0.1 millimeter from its equilibrium position and hold it in that position. A. Assume the spring obey Hooke's law. Find the spring constant K. B. How much work is needed to compress the spring 0.5 millimeter, 0.5 meter from its equilibrium. C. How much work is needed to stretch the spring 0.25 millimeter from its equilibrium position. And D. How much additional work is required to stretch the spring 0.25 meter if it has already been stretched 0.1 meter from its equilibrium position. So let's go ahead and solve this problem. So first thing, let's talk about Hooke's law, okay? According to the Hooke's law, the force required to keep the spring in a compressed or stretched position x unit from the equilibrium position is, so this is what Hooke's law said, is f of x is equal to k times x, where the positive spring constant k measure the stiffness of the spring. And note that to stretch the spring to a position x positive, a force positive in the positive direction is required, okay? And to compress the spring to a position x less than 0, then a force less than 0, which is in the negative direction, is required. In other words, the force required to displace the spring is always in the direction of the displacement. So if x is positive, then the force is positive. If x is negative, then the force is negative, okay? So let's go ahead now and start solving our problem. Solution. So we understand what does the Hooke's law said, right? So the fact that a force of 10 Newton is required to keep the spring stretched at x is equal to 1 millimeter. So we know the force, let me write everything. So we know the force of 10 Newton is required to keep the spring at stretch at x is equal to stretch at x is equal to 0.1 meter. And sorry, this was not millimeter, this is 0.1 meter. Okay. Then that means by Hooke's law, we can say by Hooke's f of 0.1 should be equal to k times 0.1, right? And f of 0.1 is 10, right? 10 Newton should be equal to 0.1 k. We divide both sides by 0.1, so our k will be equal to 100 Newton per meter. So that is k. So that means f of x will be equal to 100x. So the constant k, which we found is 100 Newton per meter. So now we can go ahead and find B, right? B, the rest is easy now because we have the force. How much work is needed to compress the spring? 0.5 meter from its equilibrium position. So the work in Joule required to compress the spring from, that's the most important because we have f of x now. So from x is equal to 0 to x is equal to negative 0.5 because we are compressing, right? Is W is equal to from A to B f of x dx. Always write the formula down so you will remember, okay? So which will be what? From 0 to, the integral from 0 to negative 0.5. Our f of x is 100 x dx. Then now we will find the antiderivative. We'll find the antiderivative of this. So which would give me 50x squared from 0 to negative 0.5. And if I substitute times 50 will give me 12.5. And see how much work is needed to stretch the spring 0.25 meter from its equilibrium position. So C is stretch. The formula will not change. So to stretch the spring from x is equal to 0 to x is equal to 0.25. Then W will be equal to the integral from A to B f of x dx, which will be the integral from 0 to 0.25 100x dx, again, which would be 50x squared 0.02 0.25. And if I substitute, you will see you will get 3.125. And then last, not the least, how much additional work is required to stretch this spring 0.25 meter if it has already been stretched? If it has already been, sorry for this type, stretch 0.1 meter from its equilibrium. So again, that's easy. D to stretch the spring from x is equal to 0.1, because that has already been done, right? And let's read again. How much additional work is required to stretch the spring from 0.25 if it has already been stretched 0.1? So 0.1. So then you want to stretch 0.25 meter again. So we need to add what? We need to add 0.25 to this one. So I will write this one so you can understand. 2 x is equal to 0.1 plus 0.25. So that's why we'll get 0.35. Okay. So basically, it's from x is equal to 0.12, x is equal to 0.35, which will be, w will be again the integral from a to b f of x dx, which would be integral from 0.1 to 0.35 100x dx. And that will give us 50x squared from 0.1 to 0.35. Use your calculator, pause, and then use your calculator again. So which would give us 5.625. So you see, if we compare part C and D, C we have what? The work need is 3.125, but again, this spring was stretched what? 0.25 meter. Same thing happened here, but it was already stretched 0.1. So you can see, comparing part C and D, we see that more work is required to stretch the spring 0.25 meter starting at 0.1 meter than if you start at equilibrium. So that's what I was trying to explain to this section. I will see you in the next section.